zou kunnen, ja, dat kan, maar ik heb er hier 10.
Oké, mag ik er dan 6 hebben? Ja, dankjewel.
Yes.
En ik vergat te zeggen, maar er is toch een commissielid online, dus we gaan nog even kort bij het scherm een foto maken.
Ah, oké.
Dus dan lopen we even voor het scherm en dan gaan we door naar de trap.
Ja, is goed.
Ja,
Ja,
wil je dat dan even doorgeven alsjeblieft?
Ja.
Ja.
So there's still one online member. So
oh, okay.
we also have to take a picture there.
Oh, when we do the group picture?
I guess they all have to be there.
Question. So I was looking at the instructions of these propositions, and can you say that once so that I can repeat how you say it?
De stellingen behoren bij het proefschrift van... De stellingen
ja. Behorende
bij het proefschrift van.
Yeah. So in theory, we have to say this before you read the proposition.
Oh, okay.
Yeah.
Maybe you should read the proposition.
No. I'm not going to be able to put up with that.
But then I have to remember.
Stellingen
Before, then I could have.
Well, I don't know if actually English the master.
How do you, I mean, instead of more like
because they will ask, if you have any propositions you want to say, right?
Het is wel A4's inderdaad te bedenken. Niet een A5'tje.
Ja, maar dit is geweldig.
Ja?
Super, dankjewel.
Okay.
Yes. Oké.
Oh, I thought they will ask a question. Or they will ask us to read a specific proposition.
Okay, we read them all at once.
We need to.
The content is finished today. Okay. And was the finishing also the last comment? Okay. In some ways, I'll be interested. But make sure that you apply for the very well, because I feel like everything there's nothing else. I know. There's a waiting list. So I know. Make sure that you do I know. That's also. Hi. You can do that.
Yeah. I'm going to ask him. So we'll start.
So when do we?
When they ask for a specific
Proposition.
proposition,
I would like to have a question regarding proposition number 5.
yeah, and then you only read proposition number 5.
Okay,
Yeah.
do I have to?
Yes, my wife.
Oh,
To see.
Yeah,
No, I just.
You're so happy with that? No.
Shall we do?
Okay, so
we do like even and odd?
Yeah, that's fine.
All right.
So I
It's okay.
No
We go after the events, we go shortly to the screen with the committee members and also with the
do you also read
and the parliament.
Did you put the books? No, I was doing it.
Yeah, for the. That's fine. That's fine.
The
bad ones.
These are all.
Okay. Yeah. Okay, yeah. Good luck.
We can start. Please sit down. Πες του να μην βγάζει με flash. Shall we start? 1, 2, can you hear me? Okay, welcome everyone. Thank you for being here in this very important day for me. My name is Sotiris Paraskevopoulos, and today I will give you a presentation about my PhD research with title Rapid Response to Contamination of Drinking Water Distribution Networks. This work in general focuses on how can water utilities better understand and better respond to contamination events in the drinking water distribution network, combining artificial intelligence and modeling of pathogens to enable decision-making during those emergencies. Let's begin. Okay, so this is the outline of my presentation. I will first start with introducing you to my PhD pathway over the last 4 years. Then we will talk about the main challenge of my research as well as the objective. The objective of my research. Then we will focus a little bit more on the 2 pillars of my research, which is about artificial intelligence to extract information from the scientific literature. And then the second pillar, as I said, modeling pathogens in the network. Of course, then we will have some key findings and takeaway messages. And finally, I will finish with some words of gratitude. Now, regarding my PhD journey, a lot of people may believe that this is how a PhD pathway looks like, you know, like a clean straight line where you have a clear path and plan, and you follow it, and then after 4 years you end up being here. But as you might imagine, this is not how it looks like in reality. In reality, this is more like it, you know, like a curved line full of challenges, full of barriers and difficulties, of course, some small victories and surprises, but you know, it looks a bit chaotic, but that was essentially how a PhD life looks like. I'm sure some of you might already know that. And then that's the whole point, is that through every challenge, you know, every challenge helps you get better and move forward, and eventually you can make it at the end. And this is my message to current and future PhD candidates, that you know, you have to hang in there, and eventually you will see the light at the end of the tunnel. All right, now let's talk a bit about science. As we said, the main challenge is about pathogens in the water, specifically wastewater entering our network and then having pathogens in water, and specifically in the tap water. And we have to realize that this is an emergency. When something like that happens, then we have an emergency, and specifically water utilities, they need to be able to preserve the health of the population of their customers. As you know, pathogens are very, very dangerous and very difficult to detect and handle, and they can cause adverse health effects. And the whole point is that time is not our friend in these situations, because water utilities must make decisions within hours and not days, because as you can imagine, if it's days, then it's already too late, then it's already over. So we need to be able to react, to respond fast. During the early stages of contamination, let's say that we have a contamination that has been detected in our network. So during those early stages, these are some of the questions that water utilities might have. You know, because at this point, we don't know a lot. We don't know exactly what is going on in our network. We don't know exactly what has happened. And then we have some high-level questions like that, like what do we know about the contamination, how serious it might be, where we should go and take samples in our network to see if there is indeed contamination or not. If there is contamination, how can we find where everything started, the source of contamination, or like how many people will be affected. So these type of questions basically are the questions that I'm trying to answer through my research. And essentially, this is the objective, as we see here, helping water utilities respond rapidly and effectively to contamination events. To do that, I had these two pillars, as you can see here. The first one is about artificial intelligence, and the second about modeling pathogens. Let's start with the first one. So what it is, the AI pillar is basically how can we use artificial intelligence to extract rapidly information. And why do we need that? Because as we said at the beginning, at the early stages, we need information, and we don't know what we're facing. So instead of going through manual literature reviews that might take ages to find out important information, what if we can use an automated approach, AI, to do this task for us, and then go instead of hours to literally seconds. So this is what I did. I developed a model using some fancy words like deep learning and NLP to train a model to extract information from scientific publications. And then we wanted to extract specific information. As we can see here, we wanted to extract 7 information keywords. That these keywords are related to pathogen characteristics. So I'm not going to go, of course, into detail, just to show you an example. So imagine that we have this text here, and then we want to find out all we can get from this text regarding the pathogen of Legionella. But we don't want to spend so much time to read all this text. So this is the information that we want specifically highlighted. So with our model, we are using our model and feed the entire information, and then we are able to go from this state to this state directly. So we can have nicely structured information about the pathogen characteristics, the symptoms, the incubation period of specific pathogens, the sources of exposure, etc. So imagine that being able to, from a vast majority of publications, using AI and then having this information in tables so that then water utilities can use this information really, really fast. So that was the first part of the first pillar. Then the second part is about comparing LLMs in a question-answer task. Basically here, what I wanted to do, let me first put this slide here. So this is, the explosion of LLMs that happened in 2021. I'm sure you recognize the logo. No, here. The logo at the top, which is ChatGPT. It's supposed to work, but not so much. Yeah, this one here. But basically, what I wanted to do is to take it a step further. Once I have completed this model, I wanted to build a model that is able to extract larger parts of text, whole sentences, not just information keywords. I tried to do that, and I failed miserably, simply because we didn't have the resources to build a ChatGPT before ChatGPT. So I said, okay, what if we can just simply compare multiple LLMs, open source LLMs, those 3 here, to compare them in a question-answer task. So let's try to find whether LLMs can answer questions related to contamination events. So we wanted to feed them with information about outbreaks, about contamination events that have happened in the past, and then we wanted to extract information related to control actions, mitigations, hospitalization. So all this information that can be very, very important and interesting and helpful to water utilities when they are trying to understand what is going on in their network. So how I did that, I'm not going to go again into details. Basically, we fed the LLMs 188 publications, relevant publications, and then we asked for each one of them, we asked them these 23 questions. You can have a look really quickly about the types of questions, and then we wanted to see, first of all, whether they can give us plausible and realistic answers, and then correct answers, and then, of course, then compare them and see which one is the best. Moving on to the second pillar, which is about being able to model pathogens in the drinking water distribution network. Here, the idea was to be able, at this point, once we have gathered all the information, at this point to be able to be as close as possible to reality in terms of modeling pathogens in the water, because once pathogens are entering the network, they are reacting with other compounds that can be found there, and then we would like to see how they spread, where exactly that they might end up, and then what does it mean in terms of a risk, like what is the magnitude of such an event, so being able to calculate the infection risk. To do that, I created this, I call it beware testbed, benchmark testbed. Basically, you see on the left, a simulation of the pathogen propagation in the network, and we can see, how it varies and spreads throughout the network. To be able to capture this behavior, we developed this model, which, as you can see, has multiple components. We're talking about the hydraulics, water quality modeling, and then consumption events also, because we wanted to capture the variability in the water demand of the people. And of course, couple this with the QMRA framework, which is the quantitative microbial risk assessment framework, in order to essentially calculate the magnitude of an event with a quantitative metric such as QMRA. As you can see here, again, the entire process, exposure assessment, dose response, health effect assessment, and then you end up with the infection risk. So that was the idea, and here we see some information regarding what specifically I did. I tried to simulate a contamination event. We see here 3 pathogens, Enterovirus, Campylobacter, and Cryptosporidium. These are 3 pathogens that represent different groups and have varying chlorine resistance, so we wanted to capture this variability. Then, as you can see here, this figure describes all the different processes that happen in the network. We're talking about once we have wastewater entering the network, wastewater contains a lot of inorganic and organic compounds that react with chlorine. So we wanted to capture this reaction. And then, of course, we have chlorine reacting with pathogens. So we have pathogen inactivation. And then, of course, because chlorine reacts with organic compounds, chlorine decays also. And it decays in 2 phases, in the bulk and the wall phase. So we also wanted to capture this. So as you can imagine, we're talking about a lot of different processes that happen at the same time. And the reason we did that is because I wanted to be as realistic as possible. And then to do that, as I said, I simulated a gross contamination scenario, meaning large amount of organic compounds and pathogen concentrations entering our network. We had 3 locations, you can see them here, and I also performed the same simulation in a chlorinated and in a non-chlorinated network to capture the differences. And then the second part of my second pillar was that once we have developed this model and it was up and running, we wanted to test it in real conditions. So what we did was that we had a case study here in the Netherlands with a water utility. And we basically try to compare, let's say, the traditional approach with the model-based approach in an attempt to find the source of contamination. That means that we knew that we had some customer complaints somewhere in the network, and then based on this, we wanted to find the contamination source. And then what we did was we simulated a tabletop exercise with a water utility, and then we asked them, okay, this is the information that you have. What would you do? How would you react? What are the first things that would you do to find the source? And we will see later on what they did and how well they performed. And then we compared that with our tool, our model that we developed, which it's through PathoInvest, which is basically, the PathoInvest is a tool, it's an application that works with the beware test bed that I created to see, whether in fact model-based approaches can help us and enable decision-making in terms of time and efficiency. Okay, I speak too fast, wait. Much better. So let's go now to our key findings regarding the information extraction task. I won't bother you with too much details, just some fancy figures here, and basically what this tells us is that we were able to create a robust model that can extract information with high accuracy from those publications, meaning that indeed we can use such models to be able to, in those situations, to gather information faster. Regarding the second part, the comparison of LLMs, we can see that, again, all the LLMs are able to perform very good in terms of evaluation metrics, precision, recall, and F1 score. So that gives us the indication that indeed that they are able to provide answers with a good accuracy. But although we had also some hallucination effects, which is basically the way that the models lie to us, in a sense that they provide answers that look plausible but are incorrect. And that was the main drawback from this approach. We see here an example. We have like these two questions, and we can see all the LLMs that were evaluated, and then we can see the variability in the responses. Some of them were able to specify an answer, some others they couldn't, and then to those that they could provide an answer, we can see the variability in the way they responded. So all in all, as I said, very, very good evaluation metrics, meaning that indeed they can be used in those situations. Regarding our infection risk, here comes the difficult part now. How am I going to explain this? Here is the chlorinated networks, or the results in the chlorinated network. We see here the three pathogens. Okay, we see here the three pathogens. Here are the three pathogens, and we see, you know, the figures how they respond in those three locations. But basically, what we need to look is this one here. So we see the differences in the infection risk. For Cryptosporidium is 45%, whereas for the others is 3.5 and 1% in all three locations. And why? The reason we see this huge difference is simply because Cryptosporidium is chlorine resistant, meaning chlorine cannot kill Cryptosporidium, whether Campylobacter and enterovirus can be killed. Then, on the other hand, we have the non-chlorinated network, where, as you can see here, because we don't have chlorine, pathogens can spread through the network, and then we see that they're able to infect the majority of the network. And then regarding the comparison of the two approaches, the traditional approach, we were able to find the contamination source using 11 samples and basically 3.7 hours until we found the source of contamination. That was a traditional one. And then, whereas on the other fact, the model-based approach, we only used 4 samples and 1.3 hours. So you see the main difference and what the difference can the model-based approach do. And then we see that also here that the infection risk is 22% for the traditional approach, where for the model-based is 12%. Again, huge difference by the time the source was identified. And then also here, again, the same information. Some key findings: AI can replace time-consuming manual literature reviews. As we said, the LLMs, they show great potential, but we must use them with caution. The developed framework can realistically simulate contamination events. The model-based solutions outperform traditional approaches. Then even with chlorination, we can still have exposure. Early detection can drastically reduce population exposure. And finally, combining any AI and modeling enables faster and data-driven decisions. Finally, I would like to express my gratitude to my promoters and supervisors, for guiding me throughout this entire journey. I would like to thank my scientific committee for reading my thesis and accepting their role, and hopefully we can have a very, very insightful discussion today. Of course, I would like to thank colleagues and collaborators from KWR and KIOS Research and Innovation Center of Excellence. And finally, I would like to thank my family and most importantly, my friends, and most importantly, my family, for always being there for me and supporting me from day one. Thank you. Okay, Bart, you scared me.
Yeah, it's 9, she said she would come at 9:50. It's 9:50.
Okay.
You realize the change in pace in the last minutes. Yes, yes, yes. Thank you, Ben.
Well, ChatGPT told me. I mean, he just basically used it to look at publications to get information.
Should I leave it like that?
What you prefer?
Yeah.
Yeah. It's beautiful, right? Yeah.
Everything went fine, so.
Okay. I will change myself and see you within 6 minutes.
Thank you.
Yeah? Okay.
That's normal. I know myself. But it's also really hot. Yeah. What I'm wearing.
Yeah, there's one professor. So that's also the teacher. Yeah, there's one teacher. I don't know, just one of them. Or one of the.
Commissie, wilt u opstaan? U mag gaan zitten.
Ik open de zitting van de commissie ter beoordeling van het proefschrift en de stellingen van Sotirios Paraskevopoulos, Master of Science in Earth Science. De verdediging zal in het Engels gevoerd worden. I request the promovendus to go to the lecture together with the Paralymps. A warm welcome for all of you at the public defense by the candidate of the dissertation entitled Rapid Response to Contamination of Drinking Water Distribution Networks. The Board for Doctorates of the TU Delft has installed a committee to evaluate the dissertation and propositions. The committee will have a debate with the candidate in public. It's an honor to present the members for the committee, to whom I extend a hearty welcome. First of all, I want to introduce Professor Prévost from Polytechnique Montreal. Then opposite of me on the table, Professor Rode Husman, University of Utrecht, RIVM. Next to her, Professor Van Gelder, Delft University of Technology, Faculty of Technology Policy and Management. Next to him, Professor Van Halem, Faculty of Civil Engineering and Geosciences. Then here at my part of the table, I have the supervisory team, Dr. Smeets from KWR, Professor Capellan from the Faculty of Civil Engineering and Geosciences of Delft University of Technology, and Professor Medema, Delft University of Technology, Civil Engineering and Geosciences, and KWR. Thank you for all taking part in the academic ceremony. My name is Luc Rietveld. It's my pleasure to chair the session on behalf of Director Magnificus. I would now like to start the opposition and give the word to Professor Prevost.
I would like to start by saying I have found the thesis to be very diverse in terms of contribution, novel AI tools, development and integration of hydraulic and water quality models through MRA, restaurant studies, and applications for management strategies. So that's a very wide and very interesting approach. There's quite a few novel points in the thesis, including the AI-based and deep learning techniques to harvest actionable and reliable evidence from the literature and to turn that into strategies to operate the system. Also really interesting is the newer model contributions to inform decision-making, integrating innovative technologies such as quick response, equalize sensors to not reduce the risk to people using this water. So, for the comments, I will start with my first question for you. We use two models to extract information. One would be learning targeted to extract quantitative and qualitative information from the scientific literature with a test case for Legionella, and then the two first chapters in my question, an information extraction model comparing three open source language model to analyze documented contamination events to provide insight on guiding response strategy. You observed very high success with the application of some of these models, and I support the shift towards data-driven models for management. Now, these models were really directed under your supervision and your supervising professors. Could any of these approaches be tailored for systems that have less resources and also less knowledgeable personnel to actually select the questions and the parameters to enter into the model?
Waarde promovendus, is this question clear to you?
Meneer de rector, yes.
Okay, then I give you the opportunity to defend yourself.
Hooggeleerde the opponent, thank you for your question. Can you hear me? I hope you can hear me.
Very well.
Thank you. So to answer your question, first of all, regarding resources, I'm assuming you mean not being able to extract information about other pathogens other than Legionella. I'm assuming this is what you mean. And to answer your question, the information extraction approach that has been developed here can be, of course, transferred to any other types of pathogens, and even not pathogens, other also chemical contaminants, all sorts of contaminations, simply because the methodology is transferable and it's straightforward. You use as an input training data that can be found in the literature, in the scientific literature. Of course, you need to make sure that the input data, the training data that you're using are of high quality, because this is what you want. You would need to have high-quality data to train your model and then be able to test it, to validate it, and see if you get results. So the main point here is to be able to get training data, all right, to get enough information in the scientific literature about the specific contaminant that we are focusing. And then once we have enough training data to train those models, we should be able to get robust results. And then regarding the second part of your question on whether we need more skilled personnel, is this correct? That was the question, right? Whether we need skilled personnel for this to answer, to create the questions. So for this, of course, you would need an expert, someone that knows exactly very well the scientific domain, so someone that knows exactly what and where to look. But of course, once this has done, then it can be used also by non-experts. So it doesn't necessarily mean that you always need to have an expert to perform these tasks. Basically, you just need an expert to provide the initial information, the initial questions, as we saw in both chapter 2 and 3, the 7 information keywords and then 23 questions related to contamination events. Of course, it is necessary to have an expert there, but after that, once this task has been completed, then it can be used also by non-expert, which is also, that's why it's very also useful, and I make the connection with the water utilities, that it doesn't require always an expert to perform this task. Thank you.
So if I understand you well, you do put forward the fact that an expert should have done it first and then made it available to others. That's really where my question was going at. So thank you. William Director, can I ask the second question now?
Go ahead.
Thank you. The final section of your research, the final test tool, is extremely interesting. It really enables quicker identification, the way you perform the results of the contamination source, the optimized contact strategies, and the rapid valve closure, the short notice collection of effects on the system. Now, could you identify the barriers to adopting such quick response strategies in most distribution systems? Can you propose also this demonstration was done with a quick response probe, other probes that are low cost and easier perhaps to deploy than the prototype you were considering? And finally, for the 3 sub-questions, if you were to select an organism, would it be Legionella or would it be another organism?
Thank you for your question. I'm not sure I understood the second question. Could you please repeat only the second question?
Okay, so what the barrier to quick response, and would there be other sensors or low-cost tools that could be used to feed the model instead of a new, very innovative tool that has not been demonstrated yet to be deployable and low-cost and potentially used easily in our systems?
Thank you for your question. To answer your question, the first part of your question regarding what are the barriers to adopt this type of approaches and technologies. First of all, for a water utility, in order to be able to implement such approaches, you need to have a GIS-based version of your network. I know it might sound easy, but that's not the case for all water utilities worldwide. There are water utilities that don't even have yet a GIS version of their network, so they can simulate and then being able to monitor the network. So the first thing that would be to have such a version of your network, and then once you have that, it's pretty easy to implement the approach. the barrier that I identified as the major barrier would be that usually water utilities tend to, as I'm also stating in one of my propositions, that they have like some sort of a risk aversion in these types of innovative technologies, in the sense that they tend to stick to what they know, they tend to use what has already been used and know that they can get results and provide results, and sometimes they can be reluctant to try a new technology. And that's totally understandable, of course, especially during emergencies. You would want to go with the option that you already know that it works, rather than trying to implement a technology that has not been tested. To answer the second part of your question, of course, the screening online, the screening tool that was used to detect the contamination in the drinking water network, of course, is not the only one. There are other also tools that can be found out there that are also able to detect pathogens, and even with greater sensitivity and specificity, if I may add. So, of course, there are other approaches. The major, at least for me, message is that we should be able to, and then now I'm connecting also to the third question, we should be able to have pathogen-specific monitoring devices, so that we don't necessarily rely on other factors such as chlorination. Because, for example, if we have a chlorinated network, then having a device that can detect E. coli won't help us so much, because E. coli in a chlorinated network would immediately disappear, and we wouldn't be able to detect it. But that would send a wrong message, because that would not mean that there's no contamination. It's just that there's no E. coli as an indicator to show us that something is in our water. And therefore, we should be able to have pathogen-specific devices able to detect all sorts of contaminations, whether we have a chlorinated network or not. Thank you.
Yeah, you have time for a short question with a short answer.
Okay.
My last question to you. With the work that you've done, especially in the last part of your work, you look at the risk of intentional or probably accidental intrusion of wastewater. What would be your recommendations for the next students to improve these evaluation of contamination during low pressure events by modeling?
Thank you for your question. I'm assuming you are mentioning pressure-driven analysis instead of demand-driven analysis, which is what I did, what I used in my simulations. Therefore, indeed, a logical next step for future research would be to integrate PDA, pressure-driven analysis, in those types of simulations, because having such a benchmark test bed, it would be very interesting to see how the PDA approach would influence the outcome, which is the infection risk, after all. Because if we had applied a PDA instead of DDA, then we should expect to see differences. Not only we should expect to see differences in the contaminant concentration, in the dilution factor, in how chlorine would decay because of this situation, and therefore we should also expect to see differences in the final outcome, which is the infection risk. So that would be a very logical and natural next step for a future student to try to integrate PDA using my benchmark testbed model.
Professor Prevost, are you satisfied with the answers to your questions?
Yes, Director.
Thank you for your position, and then I would like to invite Professor de Rode-Husman to continue the opposition.
Yes, thank you very much. Waarde promovendus. First of all, of course, I would like to congratulate you on the interesting thesis that you have written. Extending my congratulations on the thesis to your promoters and co-promoter and your family and friends. But of course, although that's a great accomplishment, I would foremost like to discuss with you about what you have put in your thesis and discuss some of your choices and statements. And the first being, health of the public should be the top priority in every emergency response mechanism. Can you first of all explain why? And could there be other priorities?
Paul Gelier, the opponent, thank you for your question. I will start with my answer, trying to answer the first part of your question. Why is it important? Why the top priority of a water utility would be to preserve the health? And that would basically, the reason behind this is because water utilities, they need to be able to provide safe water of high quality. They need to be able to maintain the integrity of the drinking water distribution network, and the whole reason of having, being a water utility, providing clean water to the population is to be able to do that throughout time, not under normal operation conditions, but also during emergencies, being able to respond fast, to restore the integrity of your network, and then try to minimize as much as possible the exposure to any type of contamination. Because especially with pathogens, if we're talking about pathogens, as I'm stating in my thesis, they can cause acute health effects. They can cause all sorts of gastrointestinal symptoms, and fortunately, in rare cases, they can also cause death. So it's very important to be able to provide clean water, because also you also want the customers to be able to trust you. And as soon as you are not able anymore to provide clean and water, people will eventually stop trusting you in that sense. Can you please remind me the second part of your question?
Well, actually, you're on your way.
Yeah, I know.
Because you talked about the trust of the consumer.
Exactly.
And I think that's a very good point. So could there be other priorities
besides
public health?
So exactly. Therefore, as soon as a water utility has detected something and they have already initiated their emergency response mechanism, of course, the first thing that they need to do is to try to mitigate the event, but also, right at the same time, or perhaps some hours later, they would need also to communicate to the public that something is happening. So this is.
But in a country such as the Netherlands, do you think people will suspect their drinking water as the source for their symptoms?
I would. I'm not sure. I don't know exactly. I'm guessing that during such an emergency would be difficult, like for customers to immediately realize that something is happening into their tap. To make sure that we have a contamination and we can identify that something is happening through hospitalizations, through complaints to the doctor, etc. That means that you need to have direct communication and open communication channels between water utilities and health agencies and first responders. And that's also one of my propositions that I'm stating that. So I think it's also very important. In that case, you should be able to detect something is happening. But as customers drinking their tap water, especially with wastewater, it's very difficult to detect that something is, is
Well,
in your water.
Yeah, actually, I think nowadays people are more on the trust than on any facts about hospitalizations and the relation with the drinking water.
Indeed.
But, well, yeah, maybe you can tell me more about it with your knowledge of AI. So furthermore, you mention focus on some pathogens. You talk about enterovirus and Campylobacter and Cryptosporidium. You all have included also some general characteristics of pathogens. But can you give some explanation on which pathogens you would think about, and did you use any selection criteria for coming up with those pathogens that you think are important in relation to the drinking water distribution networks?
Yes, thank you for your question. The main reason that I selected those three pathogens, Campylobacter, enterovirus, and Cryptosporidium, was that I tried to be as realistic as possible. Therefore, those three pathogens can be found almost all the time in wastewater, and they are also representing different groups. So one bacteria, one virus, and one protozoa. So I wanted to capture this variability, and of course, all those three pathogens, they have variability in chlorine resistance. Okay, so Cryptosporidium, we knew that is not susceptible to chlorine. Campylobacter gets inactivated fairly quickly, enterovirus a little bit less quickly. So we wanted to capture this variability, and that's why I selected these three pathogens. And of course, looking at the literature, this also helped because a lot of literature case studies, they also selected similar pathogens. Therefore, it was, for us, it was very obvious.
Well, actually, I have a question about that, because the list you made, it didn't go any further than outbreaks in 2015. So I wondered, first of all, do you think you have mentioned and found the largest outbreaks? Because I remember large outbreaks in India, for instance, on hepatitis E virus, which is very different from enterovirus. But also I was wondering, what happened in those past 10 years? Why were there no further outbreaks?
Are you referring to the table in the introduction part about the outbreaks in the Netherlands or in the rest of the world? Which one? I'm not...
both, it doesn't matter. So yeah, I think it's similar, yeah.
And then, so you're saying that the latest was the 10 years ago, that was reported 10 years ago?
Yes, so there's two parts to this question. So the first would be, if you think about those three pathogens that you selected, do you think you could come up, like in the present situation, with maybe other pathogens that you think that are important? And I agree with you on the bacteria, the virus, and the protozoa, but I think we have come a little further than that, because that's like those were the basic thoughts we had, I think, 25 years ago. And the second part of the question is, what do you think happened in the past 10 years? Because I think there have been more outbreaks, or maybe not, and why not?
Okay. Yes, now it's clear. Of course, I could have selected different pathogens. It's also a matter of how many data you can find in the literature to support the simulations. And then, to be honest with you, for those three pathogens, I was able to find enough data. I didn't want to use just one absolute value that some other had used and then use this as an input to my model. I wanted to be able to capture all sorts of variable concentrations for all three pathogens.
Yeah.
And for example, I remember at the beginning, I was also considering a norovirus, but which is similar to enterovirus, but due to the lack of enough data, we chose enterovirus, which is specifically Coxsackie virus, which we know that it's a well-known pathogen strain, and it can cause a lot of infections, and it's it's in an ongoing discussion still about their infectivity. Of course, as I said, I could have selected different pathogens, but
But would you agree with me that so it could be better water management, so we have less outbreaks, or is it because the research community just fails to publish sufficient results for you to use your model to extract sufficient data on all the pathogens and the possibility of outbreaks?
I think I agree with the second, the latter, because I also mentioned it in my the last chapter of my thesis that we need better reporting of those outbreaks. We need better protocols, perhaps standardization protocols to report incidents and outbreaks, because it's very, very difficult. And another part is that, and I also mentioned this at the beginning of my chapter, is that a lot of times outbreaks go unnoticed and are not even reported. A lot of times we have hospitalizations, we have people being infected, but they're not being reported as official outbreaks, so we cannot find them, we cannot see them. So I agree.
Okay, do we have time for one short question?
Short question, short answer.
With a short answer, yeah, thank you. So I was wondering, because you mentioned that in chapter 2 that you can use your work for information extraction on pathogen characteristics, but actually you focus on Legionella. So I was thinking, but usually these are multi-cause outbreaks with multi-solution, do you say that? No. So the solutions usually can solve many different types of problems, of issues, of the incidents. So do you think that's necessary, or to have that focus?
I think the selection of Legionella as the pathogen of choice for the information extraction was not so much related, let's say, to about being able to model pathogens in the drinking water network. Was more of let's try to build a model that can extract information from pathogens. And I knew that for Legionella, which is of course very relevant, there is enough information and training data. That was the main focus to select Legionella.
Okay. Well, anyway,
Professor De Rode Husman, are you satisfied with the answers to your questions?
Meneer de Rector, I'm satisfied with the answer.
Thank you for your position. And then I would like to invite Professor van Gelder to continue the opposition.
Dank u wel, meneer de Rector, waarde promovendus. Also on my behalf, compliments for a very well-written thesis on an important topic. I would like to discuss with you the QMRA in chapter 4. I was quite impressed by the model which you constructed and your analysis. You presented there a model to estimate the infection risks in water distribution networks by modeling the pathogen transport, chlorine decay, organic matter degradation, dose response relations, water demand patterns, etc., etc. But then if I look at your table 4.2 on page 111, then basically I see there are point estimates for all these important variables. The decay rate, for instance, is given by a point estimate. I was wondering, why did you use a deterministic approach? Have you considered to use their normal distributions, for instance, or other types of distributions for these parameters? Can you reflect on that, please?
Cochilier, the opponent, thank you for your question. Indeed, as you can see on table 4.2, I basically used specific input parameters with specific values as an input. But I would argue that the overall approach, I would think that the overall approach is a hybrid, combining deterministic and probabilistic approaches. What do I mean about that is that, of course, the hydraulic part and then the inputs that we're using here are the deterministic part, that we're using point estimates. For example, the initial pathogen concentration or the initial chlorine decay rate or the pathogen inactivation rate. These are point estimates, and they constitute a deterministic approach, but on the other hand, the stochastic water demand component contains probabilistic approaches, because it basically provides the way that we calculate water demand is by using distribution, using distributions to find specific values to determine the water demand at each node, at each time step. And then this point is different every time for every simulation. As well as the QM array, the dose response models have been determined from, again, distribution curves. So I would argue that to a certain extent, it's also probabilistic. Of course, if I wanted to take it a step further, I could probably use Monte Carlo simulations and then use multiple values for the contamination concentration, the pathogen inactivation, the chlorine decay values. Unfortunately, I wasn't able to do that simply because, not simply, but mainly because the computational time that this would require, because we have to realize that what I'm doing here, the whole benchmark, combining hydraulics with water quality dynamics and stochastic water demand, takes a lot of time, because there are a lot of reactions that happen at the same time, and then we have to calculate the hydraulics first, then we have to couple on top of that the water quality dynamics, and therefore the entire process takes already too long. For example, it took me days to calculate some of the results that you see here. So if I had to incorporate also variability in the initial values, then it would be computationally non-feasible.
Okay, and understand that. Still, it's nice to see that you did do a sensitivity analysis for all those parameters. So it's nice to see prioritization also in the sensitivity. But if you would like to prioritize all these parameters regarding the uncertainty around these point estimates, which of these variables or parameters now do you consider to have the highest uncertainty? Is that indeed the water demand, or do you think that some of these decay parameters might have more uncertainty?
Thank you for your question. As it turns out, as we can see in chapter 3, the water demand variability, the nodal water demand variability, where I introduced 10% plus or minus 10%, we noticed that it doesn't have such high variability in terms of infection risk. Like, the infection risk ranges from 1 to 3%. We don't see a lot of variability there. So water demand I would argue that it's not the parameter to have like as a high priority. On the other hand, the sensitivity analysis, which I forgot to mention earlier, as you pointed out, indicated that the most influential, let's say, parameter would be the inactivation rate and the contaminant concentration, the initial contaminant concentration. That plays a huge role. And finally, we don't see that in chapter 3, but we do in chapter 4, but we do see that in chapter 5. Another parameter that plays a major role in terms of variability and how that influences the final outcome is the valve status uncertainty. Meaning, we do see that if we don't have an up-to-date network, if we don't know exactly the valves, where exactly the valves are within our network, and we have variability there, then we can definitely see a lot of major differences in the infection risk. Yeah. So I would argue that the valve settings uncertainty is the most influential parameter.
Yeah. Yeah. In probabilistic design of systems like these kind of systems you have here, we always talk about alpha, beta, sigma. As alpha is an importance factor, beta reliability index, sigma the uncertainty, the standard deviation in your parameters. And the alpha and the sigma is exactly the balance between the sensitivity of a variable and the uncertainty in the variable. And I agree with, in fact, your recommendation by saying Monte Carlo simulations would have been a very interesting way forward here. But I also understand the computational limitations here. Now, I would like to continue the opposition with the assumptions in your model. You talk about perfect mixing, steady state hydraulics. And so you assume a constant flow velocity in your system. You don't take account for possible dead zones in your system in the distribution network. So how important are these assumptions on the infection risk estimates which you make? Do those assumptions influence it in a positive or negative way? Can you comment?
Thank you for your question. Of course, when we are developing a model, we need to make assumptions, and sometimes we need to make also simplifications. So that was, in my case, also the fact that I needed to make some assumptions on the hydraulics of the model. They do play a role, definitely, in the sense that if we have dead zones, if we have stagnant water, that would definitely have an influence on the outcome, because stagnant water means less dilution for the contamination, and that means higher contamination concentration, that means higher dose response, therefore that means higher infection risk. So I would argue that we should expect to see difference in infection risk. Now, would that be a major difference? I don't expect to see major differences due to these assumptions.
Yeah, and can that be based on empirical observations, or because that relates to the validation, in fact, of your model? And so, how to validate it with? Indeed,
if we would like to be more realistic and closer to reality, we would need to validate the results. And that's one of the drawbacks of my research, which I also stating in my chapter 6, that of course you're developing a model, but in order to be sure that it works, perfectly, not perfectly, it works to a good extent, you will need to validate it. And perhaps also use real data. But the type of validation that I performed in my research was that when so we used a model, the L-Town network from Cyprus, and then and this is an actual network. This is a real network with real hydraulics in it. And therefore, when I developed the model, and specifically the chlorine decay component, which takes into consideration the bulk phase and the wall phase and everything, we wanted to see whether indeed then the chlorine residual is also realistic. So we compare the model, the predicted values, with actual values from sensors that were installed in the actual network. And then we had readings for 1 week. And then we could see it's also in the supplementary material, I believe. And then we could see that both the predicted values are very close, very similar to the actual values. Therefore, I performed some sort of validation to a certain extent, of course.
Yeah. Okay. May I still ask one more question, meneer de voorzitter?
Very short question. Very short answer.
That's
please.
about the risk characterization in chapter 4. You do assume that the infection probability of a single individual from a single exposure event is considered as independent from the infection probability of a single individual from another exposure event, because you multiply the probabilities here. Is that a valid assumption?
Thank you for your question. I would argue that it is a valid assumption, and it's also the approach, the official approach that has been used. This formula, multiplying the multiple exposure events, is considered the most common approach, at least in my case, in the literature that I performed, like combining multiple events for the same individual. And this is how, because we had to find a way to capture the variability in the water consumption behavior. Okay, so I open the tap, I drink a glass of water, and then like 3 hours later, I again open the tap and drink another glass of water. So these two are two separate events. So, but the overall infection risk for an individual through one day can be captured with this formula.
Professor van Gelder, are you satisfied with the answers to your questions?
Yes, I am. Thank you.
Okay, thank you for your position, and then I would like to invite Professor van Halem to continue the opposition.
Thank you, meneer de voorzitter. Waarde promovendus, I've also read your thesis with much pleasure. I'm glad to step into this committee. I particularly value the combination of water quality and hydraulics, which is often missing in drinking water literature. I think it's really great that you dare to dive into that. I'd like to start with a clarification question. On page 117, you conclude that Campylobacter infection risk is more sensitive to initial concentration, whereas enterovirus infection risk is more sensitive to inactivation rate. That kind of makes sense, I guess, because Campylobacter has a higher higher inactivation rate than the enteroviruses. But what is not clear to me, does that also mean that there's actually not much of an infection risk for Campylobacter? So is it relevant, actually, that we consider that in a chlorinated system?
Calculate the opponent. Can you repeat the question just to make sure that I understand it correctly?
Yeah, so Campylobacter is more sensitive, Campylobacter infection risk is more sensitive to initial concentration. Yeah. I'm guessing that is because the inactivation rate is really fast, making the initial concentration more important.
Exactly.
But is it important?
The initial concentration.
And the infection risk.
I would argue that it is important, and we saw that also with the sensitivity analysis that I performed, that having different initial concentrations has a different infection risk, because initial concentration gets diluted once it enters the network, okay? So let's say that we have a concentration, an initial concentration of 10 to the 6th. As soon as it enters the network with a factor of approximately 3, which is what I calculated more or less, it goes directly to 10 to the 3rd. So 10 to the 3rd CFU per liter of Campylobacter or a contaminant enters the network. That has a specific infection risk. On the other hand, if the initial concentration was 10 to the 5th, having a dilution factor of 3, we would go to 10 to the 2, like 100 CFU, or maybe even less. So we can imagine that would immediately have a difference in the dose that is being entered into the concentration, and therefore the dose that is being injected for the individual, and therefore that should have a difference in the infection risk. This is how I at least try to interpret.
Yeah, and then if we compare that against enteroviruses, does that mean that the infection risk or the relevance of the infection risk for Campylobacter is important enough to take into account in chlorinated systems?
I would argue yes.
Okay, thank you for this clarification. Meneer de Rector, I have a question on proposition number 3.
Waarde promovendus, can you ask one of your paronyms to read out loud proposition number 3? It is this time an important task because we not all received the propositions.
You should have. Yes. Can you please read out loud proposition number 3, Oscar?
Proposition number 3. The presence of residual disinfectant in drinking water networks does not guarantee safety during wastewater contamination events. Chapter 4.
Thank you. Well, that's not good news, huh? Yeah. So I just returned from Kenya, where we work with Thika Water Company, a water and sewerage company, and they supply water in a situation where they can just supply a neighborhood every other day, more or less, which means that every other day there is an event, I guess. The system is not under pressure, and there's the risk of intrusion of contamination, maybe wastewater, maybe other contaminants. So could you maybe elaborate how the work you did would be relevant for a system with intermittent water supply instead of continuous water supply?
Thank you for your question. This is a very, very important topic, of course, in terminal water supply, and what does it mean in terms of outbreaks and exposure to any sorts of contamination. And it's very important also, like what I mean here, let me first start with my proposition. So basically what I mean here is that I'm not stating that the presence of chlorine residual is not working at all. It's just that it does not guarantee all the time that your system, the system is clean enough. Now, to answer your question regarding the intermittent water supply, of course, we can. That means that in such cases where we don't have a fully pressurized system, it's even more important to have chlorination in your network because these types of events happen every other day, as you mentioned. So it's very important, even though it might not be the case that the network, the water supply will be all the time cleaned. It definitely provides a barrier, the chlorination definitely provides a barrier in these situations, especially in those areas.
Mm-hmm. And then from a modeling perspective, would you be modeling all these independent events and suggest to see how they, for example, accumulate somehow, right? Because if it's an event of 24 hours and then there's no event for 24 hours and then there's an event again 24 hours, or would you go maybe for a model where you have a continuous influx of wastewater, where maybe with the parameters that you have used from a water quality perspective, you would get maybe a more reliable model? What would be your suggestion there?
What you suggested as the second option is, I would argue, what I also did to a certain extent, because in our sensitivity analysis, I also modeled 24-hour contamination, and then we saw the infection risk. So that is really, I would argue that it's very relevant to that. But I guess that also the first option that you mentioned can also be implemented. And you can even apply more variability by simply generating random events of random duration in random locations for a simulation of a month, for example. So you can run a simulation of 1 month and then apply there, as I said, multiple contaminations, which is something I may add, if I may add, that we did. Like, that's one of the advantages of having a benchmark model like the one that I developed, because recently, like some months ago, the same test bed, the same model that I created was used in a conference hackathon, let's say, where we ran simulations for a year using my benchmark, and then in those simulations, we apply exactly this one. Random contaminations of random duration and location, and then the goal, of course, there was to it was a control theory conference. So the goal was to use AI to control the chlorine injection of in the network to apply for these multiple random contamination events. So I guess I would argue that both options are valid.
Okay, well, thank you so much. I'd like to go back to the initial discussion you had with Professor Prevost, where she mentioned in the case of a resource-limited environment, and by resources I mean information limited, but maybe also financially limited, what would you need in order to apply your model and develop it for such a location, for example, in Kenya? Because that is what the first question the operator would ask you, or the plant manager would ask you.
Indeed. Thank you for your question. First things first, having a GIS-based network, it should be fairly easy nowadays because there are open source applications like QGIS and EPANET. These are free, so that means that a person with enough, let's say, expertise can easily start developing a network. So that's step number one, being able to have a configuration of your network. And then once this is done, of course, to be able to be accessible, let's say, for organizations with not so, with financial constraints, you will need to have it open source, which is my case.
May I just interrupt? What I was referring to is information related to the hydraulics in your system, which will be intermittent, so maybe even less straightforward than the steady states that are maybe also not real in our case, and water quality related measurements.
Yeah, then you would need to go to the field and take measurements and be able to monitor the hydraulics and the quality for a substantial amount of time, let's say, and then try to reenact and simulate those processes for a longer period to be close to reality. Because I could argue that you need a digital twin to have a real-time monitoring of your system, but that's not the case, and it's not feasible. So in such cases, you would need people going to the field, taking measurements, enough measurements, so you can create like enough input data, enough, let's say, input data, yes, and then based on this, try to simulate and predict with a longer simulation time.
Okay.
Professor Van Alem, are you satisfied with the answers to your questions?
Yes, I am, meneer de rector.
Okay, thank you for your position. And then I would like to go to this part of the table, to the supervisory team, and invite Dr. Smeets to continue the opposition.
Thank you. Meneer de rector, I have a question about proposition number 4, so maybe read it out.
Waarde promovendus, can you ask one of your paranims to read out loud proposition number 4?
Bart, can you please?
Proposition number 4. Models provide better solution than humans for reducing the impact of a drinking water contamination event. Chapter 5.
So, waarde promovendus, models are produced by humans. They're made by humans like you, which, if you replace that, this proposition becomes circular. Humans provide better solutions than humans. With this in mind, how would you rephrase this proposition?
Zeer geleerde promotor, thank you for your question. This is indeed, I believe, the most intriguing proposition that I had. What I'm stating here is basically that models are able to provide better solutions, and then these solutions can help humans make better decisions. I'm not stating that models should replace humans or that models are better than humans in tackling such emergencies. I'm stating that are able to provide better solutions, faster solutions, more efficient solutions, that then these can be used by humans to enable faster and better decision-making during an emergency. And we see that clearly from the outputs of chapter 5, the traditional approach versus the model-based approach. Traditional approach, what does it mean? As I said, simply, I said that in my layman's talk before, that simply we asked a water utility that this is the situation, this is a water utility, and we have a case study where we have a contamination. You need to act fast, you need to act now, what would you do? And we simply, they performed their different procedures. They initiated the emergency response, and they went to the field to take samples, and then based on human intuition and experience, which is vital, of course, they were able to find the contamination source after approximately 4 hours. On the other hand, using the model-based approach, as we see in the results, we were able to find the contamination source using 4 samples, so more sustainable, less time, and in 1.3 hours. So in that sense, I think this example really captures the essence of my proposition in that sense, that is able to provide faster and better solutions that, of course, can help water utilities.
Dr. Smeets, are you satisfied with the answer to your question?
Meneer Rector, yes, I am.
Okay, thank you for your position, and then I would like to invite the promoter, Professor Kappelan, to continue the position.
Thank you, Mynheer Director. Waarde promovendus. My question is about the artificial intelligence part of your work that you did in the thesis. So, more specifically, you use generative AI, large language models. In Chapter 2, you developed one such model. In Chapter 3, you tested 3 publicly available models, but in both cases, with the aim to extract useful information about the past contamination events from the scientific literature in order to be able to do other things better. Now, my question to you is, can you see, is this how far you would trust the AI do the job, or can you see AI being used beyond this to help better manage different stages of these contamination events?
Hooggeachte promotor, thank you for your question. It's a very hot topic, of course, the use of artificial intelligence in all sorts of domains, in our domain, of course, but in other domains also. And the ethical dilemma keeps on coming very, very top in the agendas of everyone. I would argue that, and this is also what, this is stemming also from the outputs of my research. I would argue that we should be able to use LLMs and AI in general, and they can help us, but we must use them with caution. We must always put human in the loop. We must never ever exclude, try to take out the human expert from this process. And I think this is how we should continue. I don't think that we should use AI to a higher extent, but meaning that let AI be loose and make decisions and make important decisions, especially during emergencies. Because I think for me that's the whole point, that during emergencies you can use and harness the power of AI to your advantage, but not other than that. I mean, not let it loose, but always with you, like always enable and helping the human curator or whatever.
Professor Capellan, are you satisfied with the answer to your questions?
Yes, I am, my director.
Thank you for your opposition, and then I would like to invite Professor Medema to continue the opposition.
Thank you, meneer director. Waarde promovendus, Professor Van Halem took you to Kenya. I'm going to take you to England, where last year in May happened sort of exactly what you modeled in Devon. Rain washed cow manure through an air valve into a distribution network, a chlorinated network. Was not noted until about a week later. People started falling ill in the community, many people. The infections were caused by Cryptosporidium. So the drinking water company was approached. They said, no, nothing's wrong with our water, with no E. coli there. So continued supply. Doctors even said, drink a lot of water because you need fluid replacement. So I was wondering, in this chlorinated situation, were the people better off with chlorine, or would they have been better off without chlorine?
Hooggeachte promoter, thank you for your question. It's a very important topic, and I think...
Thank you, Madam Beadle. I request the promovendus and the paranymphs to take their seats again in the public. The committee will withdraw for further deliberation in the committee room. This session is adjourned.
It's very amazing. It's a huge discussion. Chlorinated versus non-chlorinated, but at least with the non-chlorinated network, you're able to detect anything, even E. coli. If you have chlorination and E. coli will never be there because it will be immediately killed. E. coli is an indicator of fecal contamination. So if you don't have E. coli, you can't detect anything. And so far, we're able to have monitoring devices that are detecting E. coli. So the easy question would be that. But of course, there is also the other part of not having coordination, because if you have coordination, you're able to detect.
As the photographer.
Yeah, Maria. My wife and my baby. So
Yeah, I thought so.
I had a substitute.
Yeah, okay. So be careful of me, please.
I reopen the session and request the promovendus and the parliaments to stand in front of the committee. Het college voor promoties van de Technische Universiteit Delft, vertegenwoordigd door de hier aanwezige commissie, heeft na kennis genomen te hebben van uw proefschrift met stellingen en na uw verdediging daarvan te hebben gehoord, met inachtneming van het bepaalde in de Wet op het Hoger Onderwijs en Wetenschappelijk Onderzoek, besloten u de graad te verlenen van doctor. Ik verzoek de promotor door het college voor promoties als zodanig aangewezen zich wel van de hem opgedragen taak te kwijten.
Uit kracht van de bevoegdheid bij wet toegekend aan het college voor promoties verklaar ik namens dat college, hier vertegenwoordigd door de rector magnificus en de overige leden van de commissie, bij deze u, Sotirios Paraskevopoulos, te bevorderen tot dokter. En u alle rechten te verlenen welke aan de dokterstitel zijn verbonden. Ten bewijze hiervan overhandig ik u het diploma dat u het recht geeft de titel dokter te voeren. Ondertekend door de rector magnificus en de promotoren en voorzien van het zegel van de Technische Universiteit Delft.
It is the promoter's privilege to be the first to congratulate the young doctor. Professor Medema, the floor is yours.
Thank you, meneer de rector. Dear Sotirios, dear Dr. Sotirios Paraskevopoulos, you've done it. Ola kala. Big congratulations to you. Pola sinkaritiria ston patera kai miterasu. And to Chrissy and to little Iris. Let's go back for a moment to where it started. You just finished your master's thesis with Patrick, and we got the EU project Pathocert awarded. But before you were appointed as PhD, I first wanted to make sure you were PhD material, remember? So from March till June 2020, you worked on an assignment that would become later one of your first papers. But March to June 2020 was also the first wave of the COVID pandemic, so it was not so easy for you. And also for us, we had to learn to work together, work under these new circumstances. And in the beginning, you were struggling with juggling being a PhD in Delft, being a researcher at KWR, and a project partner of Pathocert, which were many things to juggle. So at that time, it was not so ola kala. But you grew, and the roles grew on you. I see a much more mature researcher and a much more mature man before me now. You combine the roles of doing good science, being dependable Pathocert project partner, and also to help implement your science and emergency response practices in Spain and in Greece and Cyprus and the Netherlands. And you gave another example where you've applied it. And it was not easy to meet all these different expectations, but you did it. You worked hard, dedicated to make the case studies of Pathocert a great success and showcase their value. And I think the two of the desktop exercises of a drinking water contamination event that we did together with Waternet and other water utilities in Amsterdam were very successful, both for you as a researcher, but also for the participating water utilities. And also a big thank you to Leon Kors and Marco Dignam and all the other colleagues of Waternet and the other utilities for that. And also I think it's appropriate to send a big thank you to the Pathocert partners, and particularly the people in Cyprus, Dimitris Eliadis, Stelios Frachimis and Marios Polikarpou, for their eagerness to collaborate with you and help you with the modeling. I look back on you and on your PhD trajectory, pride and satisfaction, and I'm sure that you do too, and you should. Ola kala. And now you are Dr. Paraskevopoulos. You and Christy planned to continue your careers here in the Netherlands, but life took a different turn, as life happens to do. Those were tough times for Chrissy and for you, and our conversation went from pathogen events to life events, and I found myself giving you advice more like a fatherly figure than a supervisor. But you adapted, and now look at your life in Greece. Your job, your family, your Chrissy, and your little rainbow baby. Ola kala.
Learn Dr. Parakevopoulos. You now have the right to use the title of doctor. Your doctorate means that society can rely on your judgment, that you will act transparently and communicate independently about your results and the social relevance of your work. In other words, your doctorate implies that you will uphold scientific integrity. I wish you a great deal of wisdom and prosperity with your new degree. On behalf of the Board of Doctorates of the Delft University of Technology, I congratulate you and your family on earning your doctoral degree. Dr. Parakevopoulos, you may return to your seat. Ladies and gentlemen, I thank you for your presence, and hereby I close this session.